All right, so these are the notes for solving 2x2 linear systems algebraically. All right, so first thing we're going to do is we're going to talk about this warm-up, and then we're going to talk about how to solve these linear systems of equations. All right, so for the warm-up, the first thing it says, the first part says to solve for y. So in this case, what we're going to do is we're going to combine our like terms on the left side, so 3y minus 4y. Now we're combining these that way so we just have one y value, and that's what we're going to try to isolate and solve. So we combine it, we got negative y, we brought down to plus 2, and it equals 5. Next thing we do to isolate the y is we subtract 2 from both sides, and we get negative y is equal to 3. Then we divide both sides by negative 1 to isolate y, and y is equal to negative 3. All right, let's go ahead and take a look at the next part here. The next part says to find y if x is equal to 3. So pretty much we're going to evaluate, and in this case we're going to substitute in 3 for x. So y equals 2 times 3 minus 1. Then we're going to simplify to solve for y. So 2 times 3 is 6. 6 minus 1 is 5. And then for the last one, it says substitute x equals 3y plus 2 into 2x plus 3y equals 4. So make sure you understand that x equals is what's solved. We're going to take this 3y plus 2, this expression, and we're going to substitute into the second equation for x. So 2 times x is 3y plus 2 plus 3y is equal to 4. Now we're going to simplify this. 2 times 3y is 6y. 2 times 2 is 4 plus 3y is equal to 4. I see we have 6y and 3y. We can combine those into 9y plus 4 is equal to 4. Now to solve for y, first thing we're going to do is subtract 4 from both sides. 9y is equal to 0. We divide both sides by 9. And y is equal to 0. So these steps right here are going to help us to solve systems of linear equations by substitution. And the first thing we're going to do is talk about the method. Just remember, we have two lines here, and they have three possibilities. They can intersect at a point, x comma y, and that point would be our solution. The lines could also run parallel, which means they never intersect. And you can actually have one line on top of the other, which will give you infinitely many solutions. All right, for step one, it says we are going to solve one of the equations for one of its variables. Now, after you solve one of them, you're going to then substitute the expression from step one into the other equation and solve for the other variable. And then last in step three, you're going to plug the value from step two into the revised equation from step one and solve. Now, really quickly for step one, there's a couple of things I always look for. First, I look to see is one equation solved. Is x or y solved? And in that case, if it is solved, I can just literally plug it in and not really have to worry about doing work. Second, I look for a coefficient, because if it's not solved, then I look for a coefficient of 1 or negative 1. And the reason why is because those are easy to solve for the variable, because either you just move something over or you move something over and divide by the negative 1, and it's pretty easy to solve like that. Okay. So let's go and take a look at these two examples here. The first one says solve the system using substitution method. So step one says solve one of the equations for one of its variables. In this case, one of the equations is already solved, right? We'll call this equation 1 and this equation 2. So equation 2 is already solved for x. Step 2 says substitute the expression from step 1 into the other equation and solve for the other variable. So I already know x equals is solved. So I'm going to substitute negative 3y plus 3 into the first equation for x. So we have 2 times, we're going to substitute in for x, negative 3y plus 3, and continue, plus 5y equals negative 5. And from here, it's just like those warm-up things. We're going to distribute. 2 times negative 3y is negative 6y. 2 times 3 is 6, plus 5y is equal to negative 5. Let's simplify the left side. We see we can combine negative 6y plus 5y, which is negative y, plus 6 equals negative 5. Then to isolate y, we're going to first subtract 6 from both sides. Negative y equals negative 11. Then we're going to divide by negative 1, and we get y is equal to 11. Now that right there is only part of this solution, because we know that intersection point has to have two parts of the coordinate x comma y. Okay, so let's go ahead and take y equals 11, and it says plug that value from step 2 into the revised equation from step 1 and solve. Well, our revised equation was a solve one. Let me write it here. X equals negative 3y plus 3. And here we can see we substitute in 11 for y. So x equals negative 3 times 11 plus 3. X equals negative 33 plus 3. And x equals negative 30. Now to write our answer correctly, all we're going to do is write it as an ordered pair. So x comes first, negative 30, comma y, which is 11. And this is going to be our solution. All right, let's go and take a look at the next problem here. So the next problem, again, we're going to label the first one equation 1 and the second one equation 2. Again, we see that x equals negative 5y minus 9 is solved, so we're going to substitute in this expression, negative 5y minus 9, for x in the first equation. Now, it doesn't necessarily have to be x being solved all the time. It could be y equals as well. We would just substitute in for y. So let's rewrite the first equation with this substituted in. Plus 3y is equal to negative 2. Then we can distribute. 4 times negative 5y is negative 20y. 4 times negative 9 is negative 36. Plus 3y is equal to negative 2. I see negative 20y plus 3y is negative 17y. Minus 36 is equal to negative 2. We can next add 36 to the other side. So we get negative 17y is equal to 34. Divide both sides by negative 17. And we get that y is equal to negative 2. Now to get the other part, we're going to substitute this into our equation that's solved. So x equals negative 5y. This time we're going to substitute directly in. It's negative 2 minus 9. X equals 10 minus 9. X is equal to 1. So my solution for this system is going to be negative 2 comma 1. All right, so there we go. Oh, sorry, be careful there. I wrote that backwards. It's x comma y, so it should be 1 comma negative 2. So be careful, small mistakes happen like that. You just saw me, I was skipped you one right there. All right, let's go ahead and take a look at the next one. So for this one here, it says solve linear systems with many or no solutions. So let's see what those special cases look like. Again, we are going to solve these with the substitution method. Let's just take a look at the first one here. So first off, this one right here, I'm going to go ahead and solve this for y. So we'll call this equation 1, equation 2. So if I were to add y to the, or add 2y, it would be x equals 2y plus 4. So this is my new equation 1. We're going to cross this one out. All right, so now this is solved. We're going to plug this directly into the second equation for x. So 3 times 2y plus 4 minus 6y is equal to 8. So 3 times 2y is 6y. 3 times 4 is 12. Minus 6y is equal to 8. So what I want you to notice here, when we combine our like terms, we have 6y minus 6y, and it removes. So we have 12 is equal to 8. Now at this point here, notice there's no more variables. So once there's no more variables, we have a case where it could be a no solution or infinitely many solutions. And it really just depends on whether the mathematical statement is true or false. So in this case, does 12 equal to 8? Well, 12 does not equal to 8. Since that is a false statement, your answer is a no solution. Okay. Now, if you were to solve one and you got a true statement like 3 equals 3, 4 equals 4, 0 equals 0, that's a true statement, and the answer would be infinitely many solutions. Now I'm going to go and take a look at this second one, solving this linear system. Since no coefficient is 1 or negative 1, this really wouldn't be a good candidate for substitution. I would probably lend itself more to elimination, but this one's a little bit tougher, and let me go ahead and show you what I would do with this problem. All right, so the first thing I would do is label my equations, 1 and 2. I'm going to go ahead and take the, let's go ahead and take the first equation. Let's go ahead and solve it for x. So we have 4x minus 10y is equal to 8. First, I'm going to add 10y to the other side. For x equals 10y plus 8. We're going to divide everything by 4 in front of the x so that we isolate x. So x equals 10 over 4 is 5 halves. Y, 8 divided by 4 is 2. So this is our new equation 1. And this is our equation 2. So now what we're going to do is we're going to take equation 1 and plug it into x right there. So we have negative 14 times 5 halves y plus 2 plus 35y equals negative 28. So let's distribute it. Negative 14 divided by, or times 5 halves, that's going to be negative 7, that's negative 35y. Plus negative 14 times 2 is actually negative 28. So let's say if I put in a plus sign, let's put minus 28. Plus 35y is equal to negative 28. So I'm going to combine my like terms. Negative 35y plus 35y, it does cancel out, leaving me with negative 28 equals negative 28. So at this point right here, once again, we have no variables remaining. We have a mathematical statement that negative 28 equals negative 28. In this case, that's actually true. So a false statement is no solution. If you get a mathematical statement that is true, then your answer is going to be infinitely many solutions. And there's the answer there. So no solution for the first one, or the false statement, infinitely many solutions if the mathematical statement is true. All right, so that's the substitution method. Now we're going to take a look at the elimination method. So this method says it's just another way to solve systems, and this one is when your equations are in standard form. Standard form of a linear function kind of looks like this: ax plus by is equal to c. All right, so first step 1 says blank one or both of the equations by a constant to obtain coefficients that differ only in sign for one of the variables. So I guess multiply one or both of the equations by a constant to obtain coefficients that differ only in sign for one of the variables. Blank the revised equations from step 1, combining like terms will eliminate one of the variables, solve the remaining variable. So you could combine the revised equations from step 1. You can add, let's go with the word add. So we're going to add the revised equations from step 1. Combining like terms will eliminate one of the variables, solve the remaining variable. And in step 3, blank the value obtained in step 2 into either the original equation and solve for the other variable. So in this case, we're going to plug. You could also substitute at that point, but we'll call it the word plug. All right, so let's take a look at our first example. Again, we're gonna label one of them 1 and one of them 2. Now, step 1 says to multiply one or both of the equations by a constant to obtain a coefficient that differ only in sign for one of the variables. This will allow us to eliminate one of the letters, or variables, sorry. So for this one, I'm looking for multiples, right? Like, if you look at the y's, 7 and 8 are not multiples of each other, but if you look at the x's, 3 and 6, hopefully you can see that if I multiplied 3 just by the number 2, 2 times 3 is 6x, they're the same, but they're not opposite, right? I'm trying to obtain coefficients that differ only in sign. So in order to make them different in sign, I have to multiply by negative 2. So when I distribute this negative 2 across the first equation, I get negative 2 times 3x is negative 6x. Negative 2 times negative 7 is positive 14y. And negative 2 times 10 is negative 20. So notice I multiplied across all parts of the equation, even on the other side of the equal sign. Now I'm going to take equation 2 and write it right underneath it. And then I'm going to add. So I'm going to add vertically going straight down. So negative 6 plus 6x goes to 0. 14y minus 8y, or plus negative 8y, goes down to 6y. And negative 20 minus 20 is negative 40. Sorry, this was an 8. So let's try that again. Negative 20 minus 8 negative 20 plus 8 is going to be negative 12. And then to solve for y, we're going to divide both sides by 6, and y equals negative 2. Now, just like in substitution, we're going to plug that value back into one of our original two equations and solve for x. Because remember, it's an ordered pair that makes the solution. So in this case, it really doesn't matter which one you pick. I'll just do the first one. 3x minus 7 times y is negative 2. 3x minus 7 times negative 2 equals to 10. 3x, negative 7 times negative 2 is positive 14 is equal to 10. Let's go ahead and subtract 14 to the other side. So 3x, 14 minus 14 cancels 0. 10 minus 14 is negative 4. From here, I'm just verifying to make sure I am good. 3x minus 7 times negative 2 equals 10. 3x, negative 7 times negative 2 is 14. We're going to 10, subtract the 14. Yep, we're going to divide by 3. And x equals negative 4/3. All right, so in this case, our final answer will be negative 4/3 for x, comma, y is negative 2. All right, let's see what we have next. Okay, the last one is going to ask us to solve using substitution and then using elimination. Now, the substitution one is set up pretty nicely. Y is already solved, so we're going to take that expression, x minus 3, and we're going to plug it in for y, since y is solved. So 4x plus 3 times x minus 3 is equal to 12. We're going to simplify the left side. We're going to go ahead and distribute this 3. 3 times x is 3x. 3 times negative 9 is 3 times negative 3 is negative 9. Like terms, 4x plus 3x is 7x minus 9 is equal to 12. We're going to go ahead and add the 9 to the other side. So 12 plus 9 is 21. 7x equals to 21. Divide both sides by 7. X equals 3. To get our last part, we're going to go ahead and sub x equals 3 into our solved equation. So in this case, y equals x minus 3. So y equals 3 minus 3, which is 0. So our coordinates are going to be x is 3, comma, y is 0. So that's substitution. Now, in the next one, we're going to go ahead and solve the system using the elimination method. So here, I have equation 1, I have equation 2. So when I'm looking at this one, I can see that the x's, they're not opposite signs, and you'd have to multiply this one by 5, this one by 3 to get them eliminated. But I noticed that 3 and 9 is a multiple of 3. So and they're opposite signs already, so I can just multiply this top one by 3. 3 times 3x is 9x. 3 times 3y is 9y. And notice 9y and negative 9y are opposites. Multiply to the other side of the equal sign. 3 times negative 15 is negative 45. Take the second equation, write it underneath it, and then we're going to combine our terms together. 9x plus 5x is 14x. 9y minus 9y is 0. And negative 45 plus 3 is negative 42. We're going to divide both sides by 14. And we get x is equal to negative 3. To get our y value, we're going to simply just plug it in to the one. None of them are solved, so let's go with the first one. 3x plus 3y equals negative 15. We're going to change this x to negative 3. Three times negative 3 is negative 9. We're going to go ahead and add the 9 over to isolate the 3y. 3y equals to negative 6. Divide by 3, and y equals negative 2. So my coordinate where they intersect is negative 3, comma, negative 2. And this concludes the notes. Do not forget to complete the homework.